Good afternoon, Matrix. It's Michelle again, and we are going to have a look at vertical projectile motion again. I hope you can remember my lesson from last week. Let's quickly recap a few things, and then we can get to work. Right. I have a summary here that explains certain things. Right. What can we learn of a displacement time graph? If you remember, last week I drew the graphs. I'm going to draw them again just now, but I just quickly want to highlight what you can learn from a graph. Right. The first thing that we can learn from a displacement time graph is that the gradient of the graph or the slope of the graph gives me the velocity. The y-intercept will give me the initial displacement, and if there are two curves that coincide, then at that point they will have the same displacement. Straight line implies that it's constant velocity, and acceleration, a curved line, shows that it is acceleration. Right. Further than that, we can learn the average velocity and the instantaneous velocity. We're not going to worry about that right now. The next thing that's quite important is a positive slope gives motion in a positive direction, while a negative slope implies that the direction is negative. Slope meaning gradient. Zero slope shows that it is at rest. And then the area under the graph doesn't give us anything. So let's just quickly use that information to redraw graphs so that we can visualize them as well. Right, let's have a look. So what happens now is, let's quickly have our three axes. There's 1, 2, and 3. Okay? We're going to have 9 graphs all in all. So let's quickly have a look at a displacement time graph or a position time graph. They said to us that if we have a straight line, it means it is constant velocity. Remember, this is position, time, position, time, position, time. Right. So a straight line like that gives me, a straight line like that means that the velocity is constant. They then went on to say to us that the slope of that graph, in other words, the gradient, I'm going to use m because we all know gradient in maths, that the gradient of that graph will give me velocity. Right. So we're going to get later on and we're going to look at the velocity time graphs, but we need to know that the gradient of that gives me velocity. The next thing we learned was that if there is a positive slope, right, then it means that it's in a positive direction. And in this particular case, we are looking at constant positive acceleration. Right. And how do we know it's acceleration? Because this graph has curved. Okay. And if you have a look very carefully at this graph, I hope I'll be able to indicate it to you, you can see that the gradient, there's the gradient, now there's the gradient, now there's the gradient. Can you see that every time the gradient has become steeper and steeper and steeper? And that means that the velocity is actually increasing. Once again, the gradient to the tangent of that graph will give us velocity. We're going to get to that later. Right. Remember, they said to us where we cut the y-axis, so in this particular case, my initial velocity would have been 0. My initial velocity here also would have been 0. Right. Now, What happens when I have constant negative acceleration, right? Constant negative acceleration. And in this case, in plain English, it means that the object is slowing down. In other words, you are covering less distance per time unit, and your graph is going to look like that. It's going to curve. It is going to have a negative gradient. Right. Have a look again at gradient. Let me show you. There's the gradient. Look at that line. Now, can you see this one is flatter? Once again. And this one is even flatter. So what has happened, if I can use my hand, the gradient was like that, and then it went like that, and finally like that. Right. So the gradient is becoming flatter all the time, or the slope is becoming flatter, which indicates to me that the object is slowing down. And once again, the gradient of that is going to give me the velocity. Right. So these are a few things that we learned about position or displacement time graphs. Let's have a look now at what we can learn from a velocity time graph. Right. The first thing we can learn from a velocity time graph is once again that the gradient or the slope is equal to acceleration. The y-intercept once again is the initial velocity, and if two curves coincide, we say that they will then have the same velocity. A straight line will imply uniform acceleration, and a curved line is non-uniform. Now, matrics, we don't do non-uniform, so you don't have to worry about that. An object undergoing constant acceleration will give us a straight line as well. So those are the things that are important. The other thing that is important is a positive slope or a positive gradient implies that the velocity is increasing in a positive direction. That means that the object is moving in the original direction. While a negative slope would imply that the object is moving in a negative direction. And another thing we learn that is quite important is the area under the curve or under the graph will give me the change in displacement or the position. Let's have a look on our graphs now. Right. So now let's apply the knowledge we've just learned to our velocity time graphs. Once again, they said to us if the object is moving at constant velocity, then it will have a straight line graph. It will not have a gradient. Right? It is a straight line graph. The second thing they taught us there, or they said to us there, was that the gradient of that graph will give us velocity. Right? The gradient of that graph will give us velocity. Then they said to us, if we have constant positive acceleration, we will have a graph with a positive gradient, something like that. Right. You can see the gradient is positive. The steeper the graph, the higher the acceleration. The flatter the graph, the lower the acceleration. Right. And once again, the gradient of this graph will give me acceleration. The gradient of a velocity time graph will give me acceleration. Right, remember this is velocity time, velocity time. Right. Let's have a look at the next graph. Remember, the gradient of this graph must give us velocity. And remember, the gradient of this graph is negative, which means that this graph would look something like that. There's a negative gradient. Okay? And then the gradient, once again, of my velocity time graph will give me acceleration. The gradient of a velocity time graph gives me acceleration. And in this case, matrix, can you see this gradient is negative? Therefore, my acceleration will also be negative. The other thing we learned here was that the area of this graph, in other words, the area of a velocity time graph, will give me change in displacement or position. And the area, once again, of this graph is going to give me displacement. Let's do an arrow that way so that you can see. Right. And the area of this graph will give me change in displacement. Right. Okay. Then the next thing we had a look at is acceleration. Now let's see if they tell us anything about acceleration here. Acceleration, well, they tell us here the slope is meaningless. It doesn't give us anything. Right. The y-intercept, once again, is the initial acceleration. If two curves coincide, they have the same acceleration. If something is undergoing constant acceleration, and remember, we only work with constant acceleration, it will be a horizontal line. And a zero slope means constant acceleration. The area under the curve also gives us change in velocity. Let's quickly have a look and apply that to our graphs. So let's see if we can draw this graph. The gradient of this graph must give me my acceleration. There is no gradient, so in this case my acceleration is 0. The gradient of my velocity time graph gives me acceleration. And remember now, very important, that the area of my acceleration time graph is going to give me velocity. The area of my acceleration time graph is going to give me velocity. Right. Now remember my last graph. My gradient is negative here, and remember the gradient of a velocity time graph is going to give me acceleration. And because my gradient is negative, it means that my acceleration must be negative. So my acceleration time graph, my acceleration is going to be negative. And once again, if I have an acceleration time graph, I can work out the area under the graph, and that area will give me velocity. Okay. It's quite a good idea, Matrix, to draw these little graphs for yourself and to have a summary of it on hand all the time. I'm going to leave this summary here, and you're going to see in a while how we use it every time. Right, now let's just quickly go back to this little bit of information that I found. Yeah, you can see exactly. I know these graphs are moving fast. But yeah, you can see, watch the graph on the left-hand side. When the graph on the left-hand side is positive, then the other two are positive as well. And when the graph on the left-hand side is negative, then the other two is negative as well. And can you see in this case, my displacement is always curved, my velocity gives me a straight line, and my acceleration just gives me a line parallel to the x-axis. Right, here you can see, once again, the gradient or the slope of a displacement time graph gives you velocity, and the gradient or the slope of a velocity time graph gives you acceleration. Then the area under an acceleration time graph gives you velocity, and the area under a displacement time graph gives you displacement. Right. I hope that that makes some sense. I like this little presentation. Right. Now let's get down to some work. Remember to keep, okay, the information I'm going to be using today, don't try and copy all of this, Matrix, because you're going to be busy forever. So what I'm basically going to do is I'm going to be discussing a worksheet with you. I will make sure that it is on the system after today, and then you can ask your teachers to please print it for you. There's a memo as well, but remember, Matrix, a memo is only used after you've actually done the work. You can't actually do the paper with a memo next to you, because then it's going to look like you always know everything. So it's important that you first actually do it, and then you compare your answers to that of the memo. Right. So don't try and copy all this down. However, a little bit later when we get to the work, you are going to physically work out this stuff. Right. When you get this, you will see, I just want to show you, it's going to look exactly like this. I know it says Grade 12 Revision 2013 on the top, but this is really a good worksheet for vertical projectile motion. And all the stuff that was examined last year in vertical projectile motion is examined this year again. So it is a good idea to make sure that you work through this worksheet. Right. Let's quickly have a look at the multiple choice questions so that you can see what type of a question they're going to ask you. They say here that a stone is thrown vertically upwards and it returns back to the thrower's hand after a while. Which one of the following position versus time graphs best represent the motion of the stone? Now, before you can answer that question, you need to remember a few things. Let's quickly remember from last week. What must you remember? You need to remember that whenever we're busy with vertical projectile motion, I'm just going to put VPM, vertical projectile motion, your acceleration is always 9.8 meters per second squared. And whether you take 9.8 as positive or negative at this point is irrelevant. I'm going to try and work with it mostly as negative today to give you an idea, but it doesn't matter. What you need to know here is that it is constant. Right. And because there is acceleration, it means that the velocity will be changing. What else must you remember from last week? That if an object leaves my hand over here at velocity x, when it returns to my hand again, the velocity is negative x. In other words, the magnitude is exactly the same, but the direction has changed. That implies another thing that is quite important. That tells us that the time up is equal to the time down. So these are a few things that we need to remember. Let's quickly go back to our graph. We are busy here with constant acceleration. So our graph will definitely have to have a curve. Remember, they give you a position time graph. And these graphs that we have here are position time graphs. Now remember, this position time graph was for constant velocity. This one was for constant positive acceleration. This one was for constant negative acceleration. This one over here. So can you see, definitely, our graph would have to have a curve. So that is something you already know before you start. Okay, so let's go back to the question and see if you can answer it. Right, we can take the position from leaving the thrower's hand because it comes back to the thrower's hand again. So it comes back to the same position. Now, can you see what I've already said to you? We know our graph must have a curve. So you immediately know it cannot be B and it cannot be D. So now our choice is A or B. It leaves the thrower's hand and it returns to the thrower's hand. In other words, it ends up in exactly the same position as which it started. Can you see that in A, they're different positions? Right. Look at C, the position is the same. In this case, the position, they've taken the hand as 0. The position is 0. So the only answer that this could possibly be is C. Hope you got that. Right. Now let's look down. Let's move down a little bit and look at the next one. A stone is thrown vertically upwards and returns to the thrower's hand after a while. Which one of the following velocity time graphs best represents the motion of the stone? Now, important. this is now a velocity time graph. It is now no longer a displacement time graph. So what do you have to do? You have to go and you have to look at your velocity time graphs. Right. We know that when we're throwing an object, it accelerates. So it can only be one of these two. Plus, what else do we know that is quite important? And I didn't mention it just now. We know that at maximum height, there where the green is, the velocity is equal to 0. Right. So now, let us quickly have a look and see if you can find the answer. Okay? Right. Look what happens in graph A. The velocity decreases until it's 0, and then it increases again. Okay. This is quite a dangerous one because a lot of you are going to want to go for that one. Right. It can't be this one because the velocity here has just decreased to 0, and after 0 nothing happened. And remember what happened when you threw it up? It went upwards, then it stopped, then it returned to the thrower's hand. So it definitely can't be C. It also can't be D, right, because according to D, it stopped. Well, it didn't stop. It stopped when it started and it stopped when it ended. Right. Okay. So, my basic choice here is A or B. Now, look at this one carefully. Remember, when you throw up the ball, your velocity does decrease, okay, until it gets to 0. Now your velocity increases again. This is why you want to go for that graph. But remember, ladies and gentlemen, the ball is falling now, which means it is now going in a negative direction. And therefore, it would be this graph. There's 0, and now the ball was falling. Its velocity was increasing, but it was negative. I think some of you might not have it. Let me just quickly go back and explain to you here. Remember what happens over here? I said to you, when the ball leaves, we took that as positive. And when the ball returned, it was negative. Because remember, it's now going in the opposite direction. And that is the reason why that part of the velocity time graph is going to be under the line. I don't want to confuse you. But if this was a speed time graph, then this one would be correct. Remember, there's a big difference between speed and velocity. Okay, let's move on to the next one. An object projected vertically upwards reaches maximum height and then returns to the original point of projection. Ignoring the effects of friction, the direction of the acceleration of the object during the motion is. Right. Ladies and gentlemen, your acceleration is always going to be in one direction. And if you have any doubt as to what acceleration is, or gravity is, acceleration, when you throw in something up, projectile motion, go outside and throw something into the air. It always falls down. So, yeah, your only answer can be vertically downwards. And that is very important. Your acceleration is always vertically downwards. Please, we tend to forget that. We want to make it up sometimes. Right, now let's look at the next one. Question number 4. A ball is released from rest from a certain height above the floor and bounces off the floor a number of times. The position time graph below represents the motion of the bouncing ball from the instant where it is released. Neglecting air resistance, which point, A, B, C, or D, on the graph represents the position time coordinates of the maximum height reached by the ball after the second bounce? Oh, people, this is a mean question. Right, let's have a look. Let's interpret our graph. Position, yeah, the position was 0. Okay, now the ball was dropped. And when it dropped, remember from our graphs, we get a curve. Okay? So the ball dropped. It then reached the ground. It actually reached the ground at A. It was then furthest away from where it had been dropped. It bounced up, and when the ball bounced up, the velocity decreased until B was reached. B is the maximum height. Then the velocity decreased. No, it increased to the ground. Right, so let's go. Velocity decreased up until B. Then it increased. It reached the ground at C again. Then it bounced and it stopped and fell down again. Right. So your second bounce is C. That's quite important. That's bounce 1, ground 1. A is ground, C is ground. So D will be the maximum height after the second bounce. Matrix, this question was tricky, not because it was difficult. This question was tricky because it was reading. And that's why it's so important that you actually read your questions carefully. There they said second bounce, right? And immediately most of us want that to be up. So we want to say A and C. But A and C are actually the ground. B and D is the maximum height. Okay. Right. Question number 5. Ooh, these are funny graphs. Right. A ball is released from rest. Okay, so immediately we know a little bit of the information. The initial velocity must be equal to 0. So that immediately throws out graph number D. You don't even have to look further because D is not released from rest. So you can immediately cross out D. Ignore the it's rest at a certain height above the floor. It bounces off the floor a number of times. Ignore the effects of air resistance. Which one of the following velocity time graphs best represents the ball? Now remember, people, our velocity time graphs, let's quickly go to that little sheet we drew. Our velocity time graphs look like this. We had that one. We had this one. And we had this one. Right. So at no stage here do we have a curved graph. So your answer can only be something with a straight line. So let's go and have a look what we've got there. We've already said it can't be D because D does not start at rest. It's not going to be B because B is curved. It's also not going to be A because A is curved. Can you see there's a curve? Right. It's going to be C. And let's quickly look at it this way. They say a ball is released from a certain height. So what happens? There the ball goes. The ball hits the ground. Right? There it hits the ground. Now remember, when